Welcome back, everyone. Today I want to talk a little bit about neurobiology and its relationship to artificial neural networks. Going back a little bit in time, the study of artificial intelligence began with some wrong premises. In the early days of AI, researchers put a lot of emphasis on things like computers that can play chess well, or computers that can prove theorems. These kinds of symbolic logical problems were thought to be kind of the essence of what makes humans intelligent. But at first they didn't pay nearly as much attention to other things that humans do, like vision and speech understanding. So any 4-year-old can do these things, so researchers kind of underestimated their difficulty. Today we know better. We know that computers are really good at chess. They can beat a lot of grandmasters at chess. They can definitely beat 4-year-olds at chess, but they can't play with toys as well as a 4-year-old. Still no. So we come to realize that symbolic thinking, rules-based symbol manipulation, is not the primary defining mark of intelligence. You know, even rats can do computations that we're very hard-pressed to match with computers. And we've also come to realize that these kinds of problems represent two different styles of computing. So there's computation that's symbolic, and there's computation like vision and speech, which is very different. Brains and computers have different strengths and weaknesses that reflect their different computing styles. Now, neural networks, artificial neural networks as we program them, are inspired by the workings of actual brains. And so let's look at a few things we know about biological neurons and contrast them with both neural networks and with traditional computation. So think about traditional CPUs, for instance. They are largely sequential in their operation. They execute a sequence of instructions. And people have been trying to introduce more parallelism into CPUs, but it's still small compared to your brain. And they are made up of logic gates that are very, very fast. It takes a matter of nanoseconds for these gates to switch. But they have the disadvantage that they're pretty fragile if some of those gates stop working. It's pretty common that just the failure of a single logic gate in a crucial place causes your CPU to stop working. Now, what CPUs are really good at, they're superior for arithmetic and for correctly putting together sequences of logical rules. They also have amazingly good memory in a sense that if you want to find something in a computer's memory, you have to know what address to look at. But if you have the key or the address to find what you're looking for, then their memory is amazingly good compared to ours. Our brains, by contrast, are very parallel. We compute things with thousands of or millions of neurons all firing at once. And that partly makes up for the fact that neurons are a lot slower than our modern logic gates. It takes typically a few milliseconds for a neuron to pass information down to the next neurons downstream. But they are very fault tolerant, which is very nice because neurons are continually dying, and maybe you've already lost a few neurons since this lecture started, but you didn't notice, and that's really interesting. It points out the fact that memories are stored in our brains in a distributed format, in a diffuse representation. So there's no one neuron whose death is going to make you forget that 2 + 2 is 4. One interesting thing about artificial neural nets that we program is that if they're trained right, they can share that resilience. brains and neural nets both seem to superpose memories on top of each other, all in the same shared weight. It's kind of like a holograph. And this isn't just speculation. This knowledge about the brain goes back to 1920 when a famous psychologist named Carl Lashley conducted some experiments where he wanted to identify where in the brain memories are stored. Specifically, he worked on rats. He trained them to run a maze, and then he would try making lesions in different parts of the brain, very precisely located, controlled lesions, trying to erase the memory trace. And Lashley failed. No matter what part of the cortex he destroyed, the rats could still find their way through the maze that they had learned to run through, no matter where he put the lesions. So he concluded that memories are not necessarily stored in one part of the brain, but are distributed throughout it. And subsequent work has confirmed this. And what's interesting is that artificial neural networks that we program on computers, if they're properly trained, can duplicate this property. Now, some of the things that brains do very well are stuff like vision and speech. These are exactly the kinds of things that modern neural networks have recently been in the news for achieving. And we also have an advantage in our memory over traditional computers. Although our memories are not as reliable, they are associative memories. And by associative memory, I mean that noticing connections between things. I mean that human beings are very good when they're presented with part of a pattern for recognizing the entire pattern or retrieving the pattern. So one thought about this is that it's really impressive to me that even though a neuron needs several milliseconds to send information on to the next bunch of neurons, we can perform very complex tasks like understanding a visual scene in about 1/10 of a second. And the ability to do that so fast is possible because neurons run in parallel, but also because of their associative computing style. So, artificial neural networks that we program on our computers, we try to get them to emulate the same parallel associative style of thinking that brains have, and thus they are the best techniques we have for a lot of fuzzy problems in vision and speech and elsewhere. But not coincidentally, artificial neural networks are inferior at traditional computer tasks like multiplying 10-digit numbers together or compiling your code. A neural network is still not the right way to do that. So what I want to do now is run through some of the biology of the neurons in our brains and tell you what the analogies are between those and artificial neural networks that we've learned last lecture, just before the break. So here is an illustration that shows you some neurons. There's, in fact, so this is a neuron, this is a neuron, this is a neuron. That's what the neurons in your head often look like. Let me give you some definitions here of what we're talking about. So a neuron is a cell. Most of them are found in the brain, but some of them are found in the nervous system as well. And they are used to aid us in thinking, and you can also think of them as communication devices. The primary way by which neurons communicate with each other is something called an action potential. That's a lot of syllables, so neurologists also call it spike for short. Same thing, but a lot easier to say. An action potential is essentially an electrochemical impulse that travels along one of the limbs of a neuron. And when that impulse goes, we say that it is fired because it goes fast. So it's an electrochemical impulse fired by a neuron to communicate typically with other neurons. And when an action potential happens, it travels along the axon of the neuron, which is a long, narrow limb coming out of the neuron. Occasionally there's more than one, but often there's just one. And so you can think roughly of the axon of a neuron as being its output. And in this diagram here, the axon of this neuron is right here. It's coming out of the bottom of that neuron, and once you travel far enough along the axon, it starts to divide up into smaller bits. In fact, it branches a huge amount, sometimes reaching 10,000 other neurons. But the early part of the axon is just one big, long limb. So one interesting thing about axons, it turns out that giant squids have a very large axon, well, relative to other cells in your brain, that they use for fast propulsion by expelling jets of water that allows them to escape from predators, for instance. And the mathematics of action potentials was first characterized in these giant squid neurons, giant squid axons specifically, and that work won a Nobel Prize in Physiology in 1963. Now, axons, if axons are the output of a neuron, then the dendrites are the inputs. So dendrites are typically smaller limbs, but there's more of them. And they are how a neuron receives info from other neurons. And where axons meet dendrites, they're called synapses. So if you come back to our figure, well, for this neuron here, you can see it has a bunch of dendrites here and here and here and here. And here is a synapse where the axon from the upper neuron meets the dendrite from the lower neuron, and that's where they make their communication. By the way, not all synapses are from one neuron to another. Some synapses go from a neuron to your muscle. That's how you fire your muscles so that you can move. And some neurons, their dendrites are connecting them to glands, or the beta cells in your pancreas. And at the synapse, we find chemicals that you've probably heard of before called neurotransmitters. A neurotransmitter is a chemical released by an axon terminal, which is the sort of like the hand at the end of the axon's limb. And the chemicals, the neurotransmitters, are used to stimulate the dendrites and maybe cause the next neuron down the line to fire an action potential as well. So let me zoom in on a couple of things that I want to explain in more detail. First of all, this is what an action potential looks like. And the way you should interpret this drawing is that the thing at the top, that is a small slice of an axon. The axon is actually much larger than that, but think of that as being a little piece of this limb, the axon. And the neuron being a cell, it has a cell membrane, and there's a voltage differential across the inside and the outside of the membrane. Normally, the outside of the cell membrane is positively charged, and the inside is negatively charged. But an action potential is an electrochemical impulse that travels along the axon, in this example from right to left, and changes temporarily the voltage inside the neuron. So what you see at the bottom, that is the actual shape, voltage-wise, of the action potential. So you can interpret this two ways. This graph showing, we start negative at the resting potential, and then suddenly we jump up very fast to a positive voltage, and then we slowly go back down to the original negative voltage. You can interpret that curve two ways. One way is just fix one point in the axon, and as the action potential goes by, that's the voltage you will measure at that particular point in the axon. But the other way we can think about it is if you walk along the axon at a single fixed point in time, that's what the voltages look like at the time illustrated here at the top. So, essentially what happens is that when the action potential reaches a certain part of the axon, you get the channels on the surface of the membrane open up and let sodium ions rush into the cell. And so as the sodium ions rush in, suddenly you have a very strong temporary positive charge inside the axon and negative outside. As the action potential continues to move on down the axon, in this particular spot, more slowly the voltage will return to normal, and that's done by potassium ions inside the cell flowing through ion channels out of the cell. So that's basically what an action potential looks like. When an action potential gets to the ends of the axon, branching out and then reaching the axon terminals, that's what I want to show you next. What we have here is an illustration of, well, the axon terminal is the thing on top here in blue, and the thing in purple at the bottom, that is a dendrite. So when the action potential reaches the axon terminal, it causes tiny containers of neurotransmitter, which are these blobs here, called synaptic vesicles, to empty their contents into the space between the axon terminal and the dendrite here. And that space is called the synaptic cleft. Once the neurotransmitters get into the cleft, they bind through ion channels to receptors on the dendrite, and they influence the next neuron's body voltage, the one at the bottom. Now, this release of neurotransmitters and its effect on the dendrite sounds incredibly slow, but it all happens in 1 to 5 milliseconds. And last thing I want to mention about that is that you have about 10 to the 11 neurons in your brain. And each of those neurons typically has about 10 to the 4, like 10,000 synapses, or 10 to the 5 after you pass CS189. Any questions about any of this? So with that in mind, I want to talk about some of the analogies between what we know about basic neurology and artificial neural networks that we program on our computers. So first, and perhaps most importantly, let's think about the output of a unit in our artificial neural network. What does that correspond to, if anything, in the human brain? You might first think, based on what I just said, maybe it's the voltage of a neuron, but that's not quite right. It's not the voltage of the neuron, it's the rate at which the neuron fires. That's the proper analogy. The frequency of firing, not the voltage of firing. Because an action potential is an all or nothing thing. All action potentials have the same shape and size. Some of them are not bigger than others. So the output of a neuron is not signified by the voltage like the output of a transistor would be. The output of a neuron is really the frequency at which it fires. And there are some neurons that can fire at nearly 1,000 times per second. That's more or less the upper bound. You can think of that as a strong 1 output. Conversely, there are some types of neurons that can, not fire at all. They can go for minutes without firing. But there are also some types of neurons that never stop firing. So for one of those, maybe you can interpret 10 firings per second as a 0. All right, with that in mind, the next thing we want to think about in a neural net is what about the weight of a connection? After all, the weights are what we're learning when we train a neural network. Well, in the brain, some synapses are stronger than others in the sense of having more influence, having maybe more vesicles with more neurotransmitter. So you can think of that as the synapse strength of any given synapse in your brain. Some are more influential than others. One interesting difference, though, between the brain and neural networks is that a neural network, a weight can equally easily be positive or negative, and it can shift from one to the other effortlessly. That's not true in your brain. In your brain, there are essentially neurons whose outputs have positive weights and neurons whose outputs essentially have negative weights. And the reason is because a positive weight is modulated by a different neurotransmitter than a negative weight. Specifically, a positive weight is analogous to an excitatory neurotransmitter. And here the word excitatory implies that if the upstream neuron fires, that increases the likelihood that the downstream neuron will also fire. The most important excitatory neurotransmitter is glutamine. Negative weights, on the other hand, they correspond to inhibitory transmitters. The word inhibitory applies that if the upstream neuron fires, that makes it less likely that the downstream neuron will fire. The most important inhibitory neurotransmitters are GABA and glycine. GABA stands for gamma aminobutyric acid. So a typical neuron is either excitatory at all its axon terminals or inhibitory at all its axon terminals. Any one neuron can't just switch from one to the other. So you could say that artificial neural networks have an advantage here. Okay, what about in a neural network, we're actually computing a linear combination of all of the inputs to a neuron. Surely that doesn't have an analog in the brain, does it? Well, actually it does. So neurologists refer to this effect in the brain as summation. Roughly what that means is that a neuron fires when the sum of its inputs integrated over time reaches a high enough voltage. But also be aware that the neuron body voltage decays over time. You know, if there's no input coming in, it will settle back down. And so if action potentials are coming in slowly enough, the neuron might not fire at all. All right, let's think about our nonlinearities. The first nonlinearity we decided to use is the logistic function, also often called the sigmoid functions in the context of neural networks. Does that correspond to something in the brain? Well, kind of, because the most important thing that the sigmoid function does is it puts an upper bound and a lower bound on the output of a neuron. So you can think of this essentially as being the neuron saturates. It can't go above a certain firing rate. Because a neuron cannot fire more than 1,000 times a second, and certainly a neuron cannot fire less than 0 times a second. So there's a range on how high or low the firing rate can be, and that puts a limit on how big an influence it can have on downstream neurons. We achieve the same thing by using the sigmoid function. All right. What about the most important aspect of neural networks at all, which is the fact that the weights change? In other words, we learn something. Well, you certainly know that human beings learn things too. How are we doing that? Well, it appears that our synapses are changing their weights in ways that are appropriate as we learn. And the ability of synapses to change their weights, as well as the ability to form new synapses, is called synaptic plasticity by neurologists. So the kind of basic principle of synaptic plasticity was articulated by Donald Hebb back in 1949, and his idea is now called Hebb's rule. So Hebb did not word it this way, but a good, short, pithy summary of Hebb's rule is cells that fire together wire together. And so, although Hebb himself didn't say it, this has become the very popular catchphrase by which people remember Hebb's rule. Now, this catchphrase does not mean that cells have to fire at exactly the same time to form a stronger connection. If the upstream cell's frequent firing tends to make another cell fire more often, then their excitatory synaptic connection tends to grow together. And there's reverse rules for inhibitory connections. And again, as I said, there are ways for neurons to grow new synapses, ways for neurons that aren't even connected to grow connections. So that can happen. Now, people have actually tried using Hebb's rule as a way of creating machine learning algorithms. And it can work, but it generally doesn't work as well or as quickly, certainly not as quickly, as backpropagation. Now, backpropagation, I would say, is one part of artificial neural networks for which the analogy is very doubtful. There's still some argument over this. There have been some proposals that the brain might do something vaguely like backpropagation, but it seems tenuous to me, and I think it's still unproven. Any questions about any of that? All right, so with that in mind, I briefly want to mention the modularity of the brain before we move on back to neural networks. So the brain is pretty modular. It's made up of all these units here. So the brain is not just like a simple, fully connected neural network where all the neurons more or less look alike. The brain is very much divided up into different areas where the neurons have different properties and traits, causing them to behave in different ways, even though there's a lot of commonalities. So different parts of the brain are structured to achieve different things. Now, the part of our brain that we think of as most characteristically human is the cerebral cortex up here, mainly made of the frontal lobe and the parietal lobe, though arguably the temporal lobe might be included as well. But this is the seat of self-awareness and language and abstract thinking, so the part you're using hardest right now. But our brains have a lot of other parts that take the load off the cortex. At the bottom, that orange brainstem, that regulates functions like heartbeat, breathing, and sleep, ones that you don't want to have to actually think about to do. And then, on top of that, we've got the cerebellum here in purple. The cerebellum is kind of the home of muscle memory. It governs fine coordination of motor skills. It saves us from having to consciously think about how to walk or how to talk or how to brush our teeth so that your cortex can focus on where to walk and what to say. Now, there's also the limbic system, which people have argued about exactly what part of the brain is the limbic system, but the biggest part of the limbic system is in the temporal lobe. And that's the part associated with emotion and motivation. Though it has to be said that the cortex plays a role there as well. And so does the brainstem, really. But emotion and motivation are especially concentrated in the temporal lobe here. And so it makes a lot of the big decisions. And I often think that 90% of the job of the cortex is just to rationalize decisions that the temporal lobe, the limbic system, has already made. Like when you tell yourself, I made a logical and rational decision to eat that 4th pint of ice cream, that's your cortex making excuses for your temporal lobe. And also particularly interesting is our visual cortex, which is here in the occipital lobe near the back of your skull. It performs a lot of processing on the input from your eyes to change it into a more useful form. And we're going to talk about it more on Wednesday because it's pretty interesting. But for several other reasons as well. Neuroscientists and computer scientists have put a lot of focus on the occipital lobe for several reasons. One being that vision is just a really important problem for computers. But also, the visual cortex turns out to be one of the easier parts of the brain to study and understand in lab animals. And one reason for that is that it's mostly a feed-forward network. It has very few loops or neurons going backward. So it's easier for us to understand, or for neuroscientists to understand, and it's easy for us computer scientists to program a computer to behave like the visual cortex. Coming back to the cortex, even though the brain overall is mostly made of specialized modules, maybe the least specialized part is the frontal lobe, which seems to be made of general purpose neural tissue that looks more or less the same everywhere. Most parts of the brain are not like that, but the frontal lobe is kind of homogeneous, general purpose computing power, at least before it's trained. And if you experience damage to part of the frontal lobe while you're still young and growing, your brain is still growing, chances are that those functions that you've lost will just relocate to other healthy parts of the frontal lobe, and you might never even notice the difference. So the last thing I want to say about neurobiology is that from the very beginning of the study of neural networks, artificial neural networks, it's been a collaboration between computer scientists and neurologists, psychologists, biologists from the beginning. Even though they come to it with different motives, they both have a lot of common ground there. Of course, we as computer scientists study neurobiology partly because we're looking for clues for how we can program our computers to behave more like human beings or to have human talents like vision and speech. But psychologists and neurologists have been part of the study of neural networks, artificial neural networks, from the very beginning too. And their motivation is they want a better scientific understanding of how we think, how do we do what we do. And studying computer models of that has taken them a long way. So are there any questions about that? All right, well, that finishes everything I want to say about biology today, but I'll come back to it on Wednesday, again, as I said, because we'll look at the visual cortex a little bit more. For now, I want to shift gears and build upon what we learned in the first neural network lecture, the one just before spring break. So I want to show you a few basic variations on that. And so I'm assuming that you sort of remember what we learned last lecture. And here's how to change things around so that you can accomplish various tasks. One of the tasks you might want to accomplish is regression, as opposed to classification. Neural networks, of course, are most commonly used to do classification, but there's lots of reasons why you might want to do regression too. You know, as I said before, in your self-driving car, you want to know how far do I turn the steering wheel to the left or the right. That's not a binary choice, that's a number that you want there. Now, when you use neural networks for regression, the most common thing that's done is to use linear output units. So effectively, another way of saying it is that you just do not attach a sigmoid function to the output units. You might still use sigmoid functions at all the internal units, or not. I'll talk about an alternative to that later. But for the output, unless you are regressing probabilities, it makes sense to not have a sigmoid at the output. However, if you are actually regressing probabilities, then keep the sigmoid because you want to keep your number between 0 and 1. A probability should not go outside that range. Now, if you make this change, just omitting the sigmoid unit at the output, then you have to change the backpropagation equations a little bit that I gave you at the end of the last lecture. I'll sort of leave that as an exercise because it only makes the derivation a little easier. So that's all I'm going to say about regression today, but coming back to classification, the sigmoid output makes sense for a 2-class classifier. But what if you want 3 classes or 10 classes because you're doing digit recognition? Then the most common thing that's done when you have a multi-class problem with more than 2 classes is to replace the sigmoid function with something called the softmax function. Now, when you use a softmax function, the idea is that we're going to deploy k different output units. If you're doing digit recognition, then we need 10 output units. And you can kind of think of each output as being the probability of that particular digit being correct. So to explain to this what it is, first of all, I'm going to introduce a variable t, which is you take the vector of hidden units and you multiply it by the weights in the final layer of the network. And so this is essentially after we have done the linear combinations in the final layer, but before we apply any nonlinearity, we have a vector t. And if we're doing, say, digit recognition and we want 10 outputs, then t will also be a vector of length 10. But t is not our output. We need to do one transformation to t. So the transformation that we're going to do is to make the output t, this vector of, say, 10 components, look like a vector of 10 probabilities. So the probability that the digit is 0, the probability that the digit is 1, the probability that the digit is 2. And those probabilities should add up to 1, because you can only have one digit, is our thinking here. So the softmax output is going to be a vector z, and component j of vector z is computed from the vector t as follows. We take the exponential of the jth component of t, and then we divide it by the sum of the exponential of all the components in t. So again, this formula is chosen because, well, it's chosen for information theoretical reasons, but as a sanity check, it has two very nice properties. First of all, each zj is strictly between 0 and 1. So we can interpret it as this is the probability that our digit is the digit j. And the sum of all of these is 1. And it's easy to see why the sum is 1. You'll notice that the denominator is the sum over all the digits of the numerators. So when you add all the zj's together, you're going to get 1. So again, let's interpret zj as the probability that our input belongs in class j. And I want to mention that if you only have 2 classes, then this is equivalent to having a sigmoid unit output plus having a second output, which is 1 minus the first output. So if you only have 2 classes, you just need 1 sigmoid output. The second output is redundant. But this does reduce to just the sigmoid in the case of k equals 2. Now, later on, I'm going to want to know the gradients of zj for the purpose of backprop. So let me just do a quick derivation here. The partial derivative of zj with respect to tj, notice that both indices are the same. That is zj times 1 minus zj. But if you take the partial derivative of zj with respect to a component of t with a different index, I'll call it t of I, then you need a different formula. It's not the same. That is minus zj zi in the case where j is not equal to I. j equals I, go back to the top formula. By the way, it's a worthwhile exercise just to work out these partial derivatives yourself after class. Are there any questions about any of this? Some of the modifications to backprop that I'm going to suggest are to deal with something called the vanishing gradient problem. Which is one of the disadvantages of using sigmoid units. And let me explain the problem, and then we'll consider some partial solutions to help mitigate it. Suppose that S is the output of your sigmoid unit, maybe a hidden unit, maybe an output unit. And suppose that that output is very close to 0, or it's very close to 1. It's not somewhere in the middle, but it's extreme. And suppose that's true not just for a few of the training points, but for most or all of the training points. What happens is, well, let's look at the derivative of S prime, with respect to its input. Remember that S prime is just S times 1 minus S. That's one of the earliest things we learned about the logistic function. Well, if S is really, really close to 0 or really, really close to 1, then S prime is pretty close to 0 too. And that's a problem because remember that when we do gradient descent, when we work out the gradients for backprop, we're multiplying by this derivative here as we do backpropagation. And if it's 0, that means that our gradient is going to be very, very small. So gradient descent is going to change S very slowly. And when that happens, we often say that the unit is stuck because it's just very hard to get it to change its input weights. And the bottom line there is that that causes training to be very slow. And sometimes it even causes you to fall into a bad local minimum and not be able to get out of it. Let me illustrate this by reminding you what the logistic function looks like. So here's the logistic function, you'll remember. For the purpose of backpropagation, it's interesting to point out where are the points where the curvature is maximum. And it turns out that the curvature is maximum when S of gamma is 0.21 or 0.79. Guess I should tell you what the axes are first. The horizontal axis is gamma. The vertical axis is the logistic function S of gamma. So I want to remind you that the reason why we use the sigmoid is we need a nonlinearity. If we had a purely linear input-output response, then the whole neural network is just one big linear combination, and we can't do anything more powerful than a linear classifier. By introducing nonlinearities, we get more power. Like, for instance, I showed you last lecture, we get the ability to compute exclusive OR. So we're interested in where the curvature is largest because we actually want to be using that part of the curve if we want nonlinearities, if we want more power than a linear classifier. So I will point out that the curvature is smallest in 3 regions. The curvature is small here in the middle. This is sometimes called the linear region of the sigmoid, even though it's not actually linear, it's not exactly linear, it's approximately linear. So if your neuron always functions within that small range, you don't have very much power yet. But that usually is only a problem if the weights are very, very small. Another reason not to initialize the weights to be too small. For the purposes of the vanishing gradient problem, what we really want to focus on is the other 2 regions of low curvature. The one up here going out all the way to infinity, which I'll call the upper flat spot. And symmetrically, there's also a flat spot at the bottom end of the curve going out to minus infinity. And so those 2 flat spots are the problem that I'm talking about today. These are the source of the vanishing gradient problem. When you are out there, because S prime is very close to 0, when you do gradient descent, you get a gradient that's very close to 0, at least as it affects this particular neuron's input weights. And so the neuron just can't learn very much. The unit gets stuck. And the more layers your neural network has, the more problematic this problem is. This is one of the main reasons why a lot of the efforts, the early efforts to train deep, many-layered networks failed. Learning is just too slow, and you wind up not being able to learn anything. Any questions about this problem before I talk about some partial solutions? So I want to say there's no perfect solution to this problem, but there are ways to mitigate it. Several things you should consider when you're programming a neural network. The first question is, when you initialize the neural network, I told you that we set all the weights randomly. But how big or small should those random weights be that we initialize the neural network with? Well, it actually depends on how many edges are coming into the neuron, or the unit, I should say. So let's suppose that the fan-in of a unit is Greek letter eta. Fan-in means the number of different edges that are coming in to the unit. Well, we initialize each incoming edge to have a random weight. And what distribution do we use? If you want to be cheap and fast, use a uniform distribution. If you want to be a little more time spending, you could use a Gaussian distribution. But either way, choose a distribution whose mean is 0 and whose standard deviation is 1 over the square root of the fan-in, eta. Or to put it another way, the variance is 1 over eta. And the reason for that is the bigger the fan-in of a unit, the more edges that are coming into the unit, the easier it is to oversaturate that unit, because you're taking a linear combination, and the more inputs you have, the bigger that linear combination is likely to be. So if you have a lot of edges coming in, you should choose smaller random initial weights. If you have just a few edges coming in, you should choose bigger random initial weights. Because the idea is, on the sigmoid curve, you do not want to be out in the flat spots. You want to be functioning in this very nice region here, where you have enough nonlinearity to do powerful things, but you're also able to rapidly change those powerful things. So the first step is make sure that the initial random weights you choose are of the right magnitude. Another thing you can do is notice the fact that if you set the labels to 1 and 0, like your output labels, then you are asking the output units to oversaturate. You're asking them to go out into the flat spot. So one thing you could do is just make the labels less extreme. You could say, oh, let's try, when something is in class C, the label is not 1, it's 0.9. When something is not in class C, the label is not 0, it's 0.1. And those are the labels you use, the vector y, to train your neural network instead of 1 and 0. Just so that you're not using your optimization algorithm to encourage all your output units to go out into the flat spot. Now, option 2 here only works for output units. It's not going to help you with oversaturation in the hidden units, but at least it can help with the output units. But since we'd like to deal with this problem in the hidden units too, here's a hack that's been suggested in the literature. This hack originates with Scott Fahlman's quick prop algorithm at Carnegie Mellon. You can modify backprop to not use steepest descent, not follow the gradient, but follow something similar to the gradient. And the way you do that is you just add a small constant to S prime. And it's reported that if you add 0.1 to S prime, that tends to work well in practice. So what this is doing is it's hacking the gradient so that it can't get stuck. Now, again, when you do this, you're not computing the gradient anymore, but you are still computing a direction of descent. It's just not the direction of steepest descent, but often it's a better descent direction that will get us to the minimum faster. Yeah? Go towards the middle. Right, so the question is, why don't we go to the middle? In a sense, we are, because this graph here, this is the graph of S. It's not the graph of S prime. Let me remind you what the graph of S prime looks like. I need to put the axis in the middle, sorry. Let's look at the graph of S prime. Remember that this is close to 0 at the extremes. It rises up to a maximum of 1/4 at gamma equals 0, and then it goes back to 0. So that's what S prime looks like. And so what this hack is doing is it's just lifting up that curve so that it is nowhere close to 0. Does that make sense? All right, cool. So here's another thing that's used quite often. This one, like option 2, is only going to work for the output units. Number 3 can work for hidden units too. Numbers 2 and 4 are only for output units. But this one works pretty well. So the simplest thing you can think of to use for your loss function is the squared error. But instead of doing that, we can use different loss functions at the output of the neural network. So the cross-entropy loss function turns out to be a really nice choice if your output units are either sigmoid units or softmax units. It's not something you should use if your outputs are just linear units. But for sigmoid and softmax, a cross-entropy loss function kind of makes more sense than squared error loss. So what's the cross-entropy? Well, suppose we're using the softmax outputs that I told you about earlier with k classes. The cross-entropy is the following loss function. The input will be two vectors, z and y. Y is the true labels for the current training point. Like, for instance, if we're doing digit recognition, y and z are both vectors of length 10, and z is our softmax predictions, and y is the actual labels that we're trying to hit. And so again, both of these are vectors of length k, one entry for each class. And the cross entropy function itself is we sum over all of the classes minus yi times the natural logarithm of the prediction zi. And if you're going to do this, I strongly recommend that you choose all the labels in the y vector so that they add up to 1. Now, if you just do the standard thing, which is, let's suppose that the digit that you're training on is the digit 2, then you would set y2 to be 1 and yi to be 0 for every I that's not 2. That's the simplest thing you could do, in which case this automatically holds. The labels sum to 1 if you do that. But remember I said in point 2 that maybe you don't necessarily want to do that. Maybe you want to set y2 to 0.9 instead of setting it to 1. Well, but you still want all 10 digits probabilities in the label vector to add up to 1. So if you're setting y2 to 0.9, you should set all the other ones to 0.1 over 9 so that they all add up to 1. So with that in mind, I'm going to go with that assumption. I want to work out the derivatives that are involved here, because if you're going to use this cross-entropy loss function, then you're going to need to work out the derivatives, and it's actually quite a bit of work to get these right. And I also want to emphasize that the derivatives I'm about to give you are only correct if this is true. The labels all add up to 1. With that in mind, let's start with the easy derivative. The derivative of the loss function with respect to zj is minus yj over zj. So that one's easy. You just take the derivative of this with respect to zj. But as we go through other parts of the neural network, things get a lot more complicated. One of the derivatives we need is the gradient of the loss with respect to rho I of the last weight matrix in the network. And so this is a I don't want to go through all the steps of deriving this, but I'm going to include one step just so that you can see what is going on. So when you work this out, answer. So the gradient we want, here's what you need to know. That's simple to understand, simple to program, but how we got there is not simple at all. The main thing I want to point out here is that the the softmax output itself is giving you these ZIs and in here and here. Sorry, the ZI there and the ZJ there. All right? And what is going wrong is that if the unit is stuck, then those are close to 0. But the cross entropy, after you take the derivatives, the cross entropy is going to divide this term by Zi, and it's going to divide this term by Zj. So essentially, this Zi cancels out this one, and this Zj cancels out this one. And that prevents the gradient from going to 0. So that's just like a simple clue that, but you're going to have to, work it out in detail yourself if you really want to understand it. But once we know the gradient of L with respect to one row, Wi, of the final weight matrix, then we can actually write an equally simple expression for the gradient of the loss function with respect to the entire weight matrix like this. And the other thing you're going to need to do backprop with the cross-entropy loss function and the softmax outputs is the gradient of the loss with respect to the last layer of hidden units. And that, it can be shown, is W transpose times Z minus Y. And by the way, I'm going to include a lot of the missing steps in the lecture note in case you want to check this, but it's also a very useful exercise to go through and understand why this is true. So but those are the derivatives you need if you want to actually implement this. Now, that's for softmax. If you just have a sigmoid output, or multiple sigmoid outputs, this works too in the following way. So first of all, suppose that you have just one sigmoid output. What we want to do is we want to have an output loss function that's the same as if we had a softmax output for k equals 2. So for a sigmoid output, we will use the loss function minus y log of z minus 1 minus y log of 1 minus z, which you will recognize as the logistic loss. And the way to think about this is that this is the same as a 2-unit softmax, because this one corresponds to the first output, and the second output is 1 minus the first output. And it turns out if you work through the math and try to compute what all these derivatives are for either one sigmoid output or even for multiple sigmoid outputs, you essentially get the same forms. You also have that the gradient of the loss with respect to the final weight matrix is again Z minus Y H transpose, and the gradient of the loss with respect to the hidden units is W transpose Z minus Y. And so should mention that here I'm assuming that Y and Z are scalars, but these work even if Y and Z are vectors, just multiple sigmoid outputs. Any questions about that? Yeah. Yeah. Oh, yeah. So if you are doing true one-hot encoding, which means that one of the yi's is 1 and all of the other ones are 0, then yeah, all of the terms except for 1 in this summation are 0. That's right. Is that understanding right? Yes, this works fine for one-hot encoding. This works equally well whether you are actually using probabilities between 0 and 1 for your labels, or just strictly using 1 and 0 labels. Much like logistic regression works that way. You can use logistic regression for pure classification, only 0 and 1 labels. You can use logistic regression to interpolate probabilities. Either way, logistic regression works just straight out of the box. So does this softmax expression. Same thing, same reasons. All right, so our fifth possible way to mitigate the vanishing gradient problem is really if you do this one, it makes 2, 3, and 4 irrelevant. And that's to just not use sigmoid outputs, yet let's use something completely different. And by far the most popular nonlinearity to use in neural networks today is no longer sigmoids. That used to be popular, but now everybody uses ReLUs instead. And ReLU is a weird short acronym for rectified linear unit. So a rectified linear unit computes what's sometimes called the ramp function and sometimes called the hinge function, which is very, very simple. Given an input gamma, R of gamma is just the max of either 0 or gamma. So intuitively, what this is doing is, here is a graph to show my nonlinear activation function. The horizontal axis is gamma as usual. The actual function itself, gamma is negative, and gamma when gamma is positive. So very, very simple looking function. Obviously very easy to compute. Obviously its gradient is dead simple to compute too, because the gradient is 1 when gamma is positive and 0 when gamma is negative. What about when gamma is exactly 0? Well, then the derivative is not defined, but we pretend that it is. For the purposes of gradient descent, you can pretend that the gradient at 0 is 0, or you can pretend that it's 1, or you can pretend that it's anywhere between 0 and 1. Doesn't matter much. Gradient descent will work fine. So just for simplicity, let's say that it's 1. All right, so this is the popular unit these days, and it is particularly popular for many layered networks, especially when you have large training sets. So one nice thing about ramp functions, obviously, is that they're very easy to compute. The gradients are very easy to compute. You know, computing exponentials is a little bit slow. It's not that slow compared to backprop as a whole, but if you don't have to compute exponentials, that speeds up things a little bit. But what's more important is that ReLUs just work better with really deep networks, that the vanishing gradient problem vanishes, so you have no longer the problem of your gradients are too small and you get stuck. Now, one criticism you might have when you see the ramp function is you might say, well, that looks almost linear. Is that nonlinear enough to be powerful? And it turns out in practice, yes, it is. You can compute exclusive OR and all kinds of other very difficult things with ReLUs. A question? Why is the flat region on the left what?
Not a problem.
Why is this not a problem? Well, it could be a problem. So obviously, if you are in that flat region, your gradient is 0. So, but the question isn't, you know, is your gradient sometimes 0? The question is the gradient 0 for the vast majority or all of the training points? Now, if you have a situation where, let's say, 1/3 of your training points are in the, put this neuron in the positive region, and 2/3 of them put it in the negative region, you're fine. The thing that would go wrong is that if almost all of your training points are sitting in this region, then this neuron might get stuck. It might not be able to learn anything. That doesn't seem to happen very often in practice. I'm not entirely sure if it's understood why, but practically speaking, ReLUs are much less likely in empirical use to have problems with vanishing gradients than sigmoids are. There is another associated problem, though, which is you'll notice that the output of a ReLU can be arbitrarily large. Since we're not using a sigmoid anymore, we're not clamping an upper limit of 1. We're not clamping any upper limit at all. So you might ask, can it get too big and saturate units downstream? And sometimes it can. And this leads to a different problem called the exploding gradient problem, kind of like your gradient is too big instead of too small. This is not a big problem in shallow networks. It can become a big problem in deep networks. It can become an even bigger problem in recurrent networks where you have a loop. Just a reminder that if you're choosing option 5, then options 2, 3, and 4 are no longer relevant. Options 2, 3, and 4 are specifically designed to work with sigmoids. But option 1 is still relevant. So with ReLUs, you still need to think about what your random initial weight should be. However, it has been shown, and if you're interested, I can tell you the paper on EdSTEM or something, that if you, when you do ReLUs instead of sigmoids, it's better to choose ones with a standard deviation of 2 over root eta. So 1 over root eta, that's for sigmoids. 2 over root eta works better with ReLUs. There is theory to support this. Just thought you should know. Any final questions? All right, thank you very much.